Welcome back. This is Larry Benko, W0QE, and this video is about RF monitoring circuits. It's been a while since I've done a video, and I've started several, but every day if the weather is warm, I end up mountain biking up in the hills, and the videos get delayed. With the weather finally becoming colder, I hope to catch up here soon. Having a circuit which can be inserted into the output of a transmitter or the input and output of an amplifier for the purposes of monitoring signal power, distortion, harmonics, output overshoot, IMD, spurious signals, circuit gain, etc. can be quite useful provided that the monitoring circuit itself has no effect on the RF signal. Before we start analyzing circuits such as the one shown here in the picture, let's look at the possible ranges of voltages and currents that we might encounter. This simple circuit shows a three-component circuit. The load component is just a resistor. The transmission line here represents anywhere from 0 to a half a wavelength long at the chosen frequency. It's a lossless piece of transmission line here, 0 for loss. And we can see that when the transmission line is of length half wavelength, 180 degrees, we get a full rotation. This means that as we would change the length of the transmission line in series with this 150 ohm resistor, we could get every single impedance that would be represented by a 3-to-1 SWR. So in this case right here, we have a 1500 watt generator which has an output impedance of 50 ohms. That's the UZ0, means it's a 50 ohm output impedance. So it produces a maximum power output at a 50 ohm load. Anything else is less than the 1500 watts out. We do two simple plots. One, we plot the voltage right here from T1 to ground, which is right there, the magnitude of T1 dot capital V, and we plot the magnitude of the current here going into T1 as T1 dot I, and we're done. So here's the plot of the impedance. Here's the plot of the voltages. Now what we see is we see a power output, which is the pink line here, of 1125 watts right there. That is 3/4 of the power of 1500, and it's 3/4 because at a 3-to-1 SWR, the reflection coefficient is 1/2. 1/2 means 1/4 of the power comes back, and 3/4 gets to load. 3/4 of 1500 is 1125, and etc., etc. We see a maximum voltage here of 411 volts, and we see a maximum current of 8.2 amps. Both of those are considerably higher than what we would see at 50 ohms. At 50 ohms, we see a 273 volts. They lined up on top of each other, and 5.47 amps. So again, we're trying to look for maximums and stuff here for the circuit we want to build. So this is one possible maximum. Another possible maximum that may make a little more sense is if your transmitter or your amplifier has an output network that can be adjusted, you might continue to be able to get the power, the full power, in this case 1500 watts, into the load with some SWR. So if we assume we're going to allow a 3-to-1 SWR, which is what this 150 ohms is in series with this variable piece of transmission line, what we're doing here is we're sweeping the transmission line from 0 to 34.88 feet, so we encompass all the lengths that are necessary to do a full half wavelength. We could set this generator type to be an X-match. An X-match can be thought of as having a lossless matching network inside. So in this case, we will see a maximum of 474 volts in voltage, a maximum current of 9.48 amps. I'm calling those the maximums in my case. In your case, if you want to do something different, 100 watts, 5 watts, 1 watt, you do whatever you would like to do. SimSmith calculates it just fine. In my case, on a minimum, I wanted to be able to say I had a 1 watt generator. It did not have a matching network in it, which gives me a lower answer when I'm done. I'm going to come over here and I'm going to calculate the voltages and currents. And what I get in this case, since it's on the bottom end, I want the minimum. The minimum voltage here will be 3.5 volts, and the minimum current will be 70 milliamps. I did this in a spreadsheet also which is probably a little bit easier to see. But it shows a maximum of 474 volts, a maximum of 9.49 amps, a minimum of 3.5 volts, and 70 milliamps. If we call those our maximums and minimums of our monitoring circuit, we have a voltage that's too large to put into any kind of a receiver, or current that's too large to put it into any kind of a receiver. And we have voltages and currents down here that are on the range of being too large to go into a receiver, but not necessarily would damage it 100% of the time. But it's still a huge signal. If we take these signals and we want to do something to them, our monitoring circuit should take a fraction of the signal that we see and send it out to a port where we can put our receiver, our spectrum analyzer, our oscilloscope, or whatever. In this case, I decided let's do 40 dB. 40 dB has a really nice characteristic. It's 1/10,000th in voltage, or excuse me, 1/10,000th in power, but it's also 1/100th in voltage and 1/100th in current. So it calculates in your head very nicely. So if we build a circuit that had a coupling factor of 40 dB, what we would see is our 474 volts would become 4.74 volts. Our 9 amps would become 94 milliamps. And down on the low side, our 3 volts would become 35 millivolts. And our 70 milliamps would become 0.7 milliamps. And if we drive a 50 ohm load with those values, we see that on the high end we have 26.5 dBm, and on the low end we have minus 16 dBm. These values still may be too high for a receiver. They're pretty good for a spectrum analyzer. A spectrum analyzer typically will take up to maybe plus 30 dBm. If they're too big for your spectrum analyzer, you may need to put a couple dB attenuator before the spectrum analyzer. They're a little bit large for a receiver. Another 20 dB attenuator for a receiver would be fine on the output. But 40 dB represents a nice number. So for the purposes of this video, I'm going to say my goal for building this circuit is a 40 dB coupling. Again, you do as you wish based on what you would like to, monitor and what power levels you would like to monitor. Shown here are various circuits and schematics that we might wish to use as candidates for monitoring an RF signal. The 4 on the left here in the picture are 4 I've built myself and actually used. They have various characteristics which makes them more or less suited at different times. This is a commercially available one. But they all fall into one of 3 categories. And the categories are voltage monitors, current monitors, and power monitors. Voltage monitors take a voltage that's on the line and they pick a fraction of it off to send to our monitoring equipment. That fraction can be picked off with resistors, capacitors, inductors, a transformer, whatever. But the goal in all of these cases is to have the pickoff point be a high impedance, the pickoff point at the line be a high impedance, converting that to a lower impedance and lower amplitude output to send to our spectrum analyzer, receiver, whatever oscilloscope for whatever we wish to use to monitor the signal. The current monitor works the same way, but instead of picking off a voltage with a high impedance point, we want to take a sample of the current with a very, very low impedance, transform that up to a higher impedance, which gives us some voltage, and send that out to our monitor port. Finally, there's power monitors. Power monitors are devices that look at both voltage and current on the line. They sum those up and they can determine which direction the power is going. We think of these generally as SWR bridges, but you don't have to actually demodulate the output. You can leave the output as an RF signal here and look at it with your monitoring equipment. The one on the left is typically referred to as the tandem match type bridge, because that's where the circuit first appeared. The one on the right is typically referred to a Bruni bridge, and named after Warren, I believe, Bruni, who, I hope I have the pronunciation correct on that, who designed a circuit similar to this in some Collins equipment originally. This is not the exact circuit of the original Bruni bridge, but it's the one we see most often in amateur radio. But they all have various characteristics. Our goals here or my goals at least, and depending on what you'd be looking for, your goals may be similar to mine and may not be. But wide frequency range is good. If it has a wide frequency range, we have the ability to look at the harmonics on signals, which is a nice thing to do and something we need to do a lot of times if we're building an amplifier. Constant coupling versus frequency. The monitor port needs to be some number of dB or some percent of the signal that we're monitoring. And it'd be nice if that would be fixed with frequency. If it's not fixed with frequency, you can correct for it. But correcting for it is a constant annoyance. And it causes errors in our, in the work we do and stuff. So consequently, it's nice to have that be constant. I mentioned in the previous slide, 40 dB is a nice number, I believe. And the reason for that being that it's 1/100th. But nevertheless, whatever value you use, it really doesn't matter. But it's nice if it's constant. I've set my goal to be 1500 watts at a 3-to-1 SWR, all impedances I want to be able to monitor. It needs to have very low insertion loss. All these circuits here have very low insertion loss. They need to also have low insertion SWR. The circuit itself cannot alter the SWR on the line appreciably. And consequently, that's the reason why all these impedances up here needed to be high. That impedance needed to be low, and that type of stuff. It'd be nice if the output port was a 50 ohm port. The monitor port was 50 ohms. It's easy to drive coax with 50 ohm source. It works nicer into general equipment. If you wish to put some kind of a filter out there, the characteristics of the filter are proper. If you drive it with a source that doesn't have the right impedance, or a load that's not the right impedance, then a filter wouldn't have the characteristics you thought it might have. And it'd be nice if it was easy to build without special equipment. That doesn't mean you don't have to be careful how you build it, but it'd be nice if you could build it without special equipment and not need to have to measure it. Someone else had done that work for you. So those are the goals. And these circuits on the left here, this circuit and this circuit, both are the tandem match circuit here. This circuit and this circuit are both the current monitors. This one could be thought of as being a voltage monitor. It's just back-to-back two SO239s with a short piece of wire and some threaded aluminum standoffs that are pushed together, and you can go in here with a oscilloscope probe and connect. And that is not nearly as good of a monitor as you might think it would be. But we'll look at all these monitors in more detail. Let's first look at a direct connection type of a monitoring circuit. We have a 50 ohm generator and a 50 ohm load. And for these purposes, we're going to assume the connectors are perfect, so they don't do anything to the 50 ohm circuit at all. What kind of an impedance could we put in shunt with this circuit that would allow us to have a good SWR? Well, 50 ohms obviously caused the SWR to go out of sight. Let's raise this number up and see what we can get. If I assume that the biggest SWR I want to allow is 1.05 to 1, basically we're talking about something in the order of about 1,000 ohms. 1,000 ohms of resistive shunt will give me a 1.05 to 1 SWR. Likewise, 1,000 ohms of inductive reactance will give me just a hair over 1.05 to 1 SWR. And 1,000 ohms of capacitive reactance would give me, again, just a hair over 1.05 to 1 SWR. If we assume that that's the maximum amount of SWR increase that we would tolerate in our circuit, let's see what we can do. I'm also assuming for the moment that I'd like to make it all the way to 300 megahertz because I want to look at harmonics of an amplifier that might be a 6-meter amplifier. So, with that having been said, this is a stake in the ground as far as what the impedance needs to be. It needs to be at least 1,000 ohms or more, or we won't be happy. Now, while we're doing this, I showed a circuit before that was two SO239 connectors butted up together with just a short piece of wire in between them, and I mentioned that you could use an oscilloscope to monitor the voltage. Well, let's look at that for a moment. The voltage we'd see here, as we calculated before, with a 1,500 watt load of type X match, so that we are actually matching to the impedance and get the full power out. shows 1.5 kilowatts in 150 ohm resistor, and it shows us as having 474 volts here, which is what we calculated before. Some digging around, found a couple interesting data sheets. Here's an old Tektronix probe. A 6009 was probably the go-to probe for 20 years, 10-to-1 probe. And they have a specification on it. That probe is good for 2,000 volts peak up through 200 kilohertz. And then it tapers down to about 1,000 volts peak through the lower part of the HF region, and then it drops after that. By the time we get to 100 megahertz, we're looking at somewhere around 50, 60, maybe 65 volts peak. 65 volts peak, 40-something volt RMS. That's the maximum that probe can do, independent of whether or not your oscilloscope says it's 50 volts per division or not. That's the maximum that the scope is rated at. Additionally, if we look at the impedance of the scope probe at 100 megahertz, we see it's about 18 kiloohms in parallel with 2, 3, 4, 5, maybe 550 ohms. 550 ohms in parallel with 18K is, ignore that, it's 550 ohms of impedance. As we saw just a moment or two ago, 550 ohms it does not exceed our 1 kiloohm that we were asking for. As an additional point of reference, they talk about the probe having an impedance of approximately 50 kiloohms at 1 megahertz. The probe is primarily capacitive by the time you get to a megahertz. So it's 50 kiloohms at 1 megahertz. It'd be 5 kiloohms at 10 megahertz or 500 ohms at 100 megahertz, which is very close to the 550 ohm number that they show. So this probe is not rated for the voltage, and it's too low of an impedance. Even though it's a 10-to-1 probe, we think of those generally as a 10 megohm probe. Another data sheet. This data sheet is for a probe that comes off of a 350 megahertz Rigol probe, and they show the maximum voltage as being 300 volts RMS down low. That's not a probe limitation as much as it is an IEC Category 2 limitation. But they show it continuing to drop off. So by the time we get to 100 megahertz, we primarily have, it's hard to read this graph, but if there's 0 and there's 50 volts RMS, we're looking at maybe less than 20 volts RMS at 100 megahertz. So with that being the case, this probe again is inadequate to look at the 470 volt number that we talked about. And it has the same kind of impedance limitations that the Tektronix probe has. I didn't see it in the circuit, but what we've got is it's the same. All 10X probes are the same kind of construction, so it doesn't have a high enough impedance either. So both of those probes are inadequate, and I suspect just about every probe out there is. There's some special differential probes and active powered probes that can look at high frequencies and still have high impedance, but most of those will not be rated for high voltage also. So this kind of says to me that it's pretty obvious that a direct connection is a little bit iffy. Now, if you're running lower power, particularly QRPs, you're fine, and maybe even up to 100 watts, you're okay, but you have to look at your own probe and see what you've got. So the direct connection is kind of not really a good way to go, in my opinion, but it makes for an interesting discussion. Here's a circuit of a resistive probe. As mentioned before, we'd like to have 40 dB of coupling, where the coupled port is 40 dB down from the actual voltage on the line. And through a little bit of math here, I came up with these two resistor values, and it shows us as being 40 dB down. And this 40 dB number is measured, letting SimSmith do the work again for us, as it's the ratio of 10 log of the power on the output of this resistor here that goes to the monitor divided by the power at the load. Now this circuit shows an internal 2.5 k ohm resistor, a 51 ohm resistor, and then a 50 ohm load out here. So X here is your cable that connects between your monitoring circuit and your device that's making the measurement. Another thing is, this circuit has a 50 ohm output impedance. We can prove that a couple different ways. Probably the easiest way is just to let SimSmith make the calculation for us. Like this. We terminate this point at 50 ohms and 50 ohms on this side, just like it would be done normally. We let SimSmith look at this point here, and we look at the SWR. So let's turn everything off, look at the SWR. We can see that the SWR is incredibly low. Now, there's stray capacitances and all kinds of stray inductances and stuff, but it shows us that these two resistors are the right value to give us a 50 ohm output impedance. So this circuit starts to look pretty nice. However, I also plot the power in these two resistors, and if you wish to handle the power that I wanted to handle, which was 1500 watts into a 3-to-1 SWR, here's 1500 watts into 50 ohm SWR, and we measure the power here. We see that the power on resistor R2 is less than 0.2 of a watt, which is great. But the power, unfortunately, on R1 is 28.8 watts. Trying to put 28.8 watts in a small package is not going to work. First of all, any kind of resistors that you put here would have to be resistors that were heat sunk. Heat sunk resistors have 3 or 4 picofarads of capacitance on them. You can put 3 or 4 picofarads of capacitance in this circuit from, say, the midpoint of this resistor, and you can see that the SWR will become ridiculous. Nevertheless, even if you could do that, putting 29.4 watts in a small little box is just not going to work. However, this circuit is a reasonable circuit to use for purposes of lower power and certainly for QRP. At 100 watts, again, no SWR, 100 watts, we would find that we need just about 2 watts on that resistor. So we could make that work. So it was a low SWR environment. We were going to test that, and 100 watts, we could use this circuit quite nicely. Of course, it works great at QRP. The SWR of this circuit is absolutely great too. All right, what's going on here? 1.02 to 1. Less than 1.05 to 1 that we talked about earlier. So it's a good circuit. It's a doable circuit. Everything's fine. You just can't run it at high power. So for that reason alone, I'm going to strike it off the list. The next circuit we have to look at is a capacitive voltage divider circuit. And the capacitive voltage divider, much the same as the resistive voltage divider, uses two components whose impedance is not fixed, but it tracks with frequency. Therefore, the percentage you have right here of voltage, an open circuit voltage here versus what's on the line, will remain constant with frequency. However, if we drive a 50 ohm impedance with it, we see that the coupling factor doesn't stay the same with frequency. So in this case, I made the upper capacitor 5 picofarads, the bottom capacitor 495, which gives us a 100 to 1 voltage divider. And we see our 40 dB coupling factor plotted the same way I plotted it in the past on the other circuits. But at low frequencies, where these impedances start to rise, and they're no longer, the combination of these is no longer low to drive 50 ohms, what we start to see is a drop-off in coupling. This drop-off in coupling means you have to compensate for what frequency you make a measurement at if you want to do harmonic measurements. We can play with this circuit some and make it a little bit better, but basically we also have a problem here with the SWR. The SWR has risen to be 1.6 to 1 at the upper end of the frequency range. That may not be really that bad, but it's a lot worse than I wanted it to be. So the way we make the frequency better up here, the SWR better up here, is to make the capacitance smaller, but that exacerbates the problem of the roll-off in coupling. So what we can do is we can make the capacitance here a little bit larger, actually. Let's make it like maybe 7 or 8 picofarads. We're going to make this, I don't know what's some value. It's going to be a different value than it was before. But what we're going to do is we're going to compensate for the SWR by either having some wire in series with the some length of wire in series with the components inside, or think of it as a transmission line as we did before. But I'm going to do it right now as inductors. We'll let them both be the same value. Better let them both be L1. And we can see as we start to take L1 and move it around, we start to see we can do a pretty good job of compensating for the SWR. And we see a little bit of a rise in the coupling factor up here. It's not 40 to 1. It's not 40 dB anymore because this is not the right value capacitor. But something like that. It rises a little bit up here. It still falls off down here. With more capacitance, we can play some games, and this may not be successful, but I'm kind of guessing at this. We have to isolate the 50 ohm load out here from this impedance right there. So we can do it by putting some kind of like an L network, an L pad here. Whoops. And we need to make R1 a pretty big value resistance to, and R2 has got to be above 0, of course. Okay, what we see here is we're going to have a hard time getting up to 40 dB. We can make this capacitor smaller. And as we make it smaller, we still roll off down here, but you can play with this a lot. I've done some playing around when I made this file. But if I'm willing to tolerate a loss, say like 55 dB, I can make my circuit be pretty. I can't really make it to be that good. Maybe if I say I'm going to tolerate 60 dB. Let's go to 60 here, move that up a little bit. Make it 1 dB per division. So we see it vary between 59 dB and about a little bit under 61. So that's really not that bad, but it's not a 40 dB coupling anymore. We ended up having to attenuate the signal a lot more, and that may not be acceptable. Personally, I don't like this scheme very much, but this could work. In the past, I've done this many times where I just take two capacitors to couple a signal to some kind of like a spectrum analyzer or something like that. But I'm generally not looking at harmonics. This would allow me to look at harmonics and I can correct for it a little bit if I needed to. But it's not much of a correction. So you might say this is tolerable. I don't really like it that well. But what we have is we have this basic problem, and that is we're using two components here over a wide frequency range. They need to be low enough impedances that they can drive something, but which is easy to do up at the higher frequencies, but at the low frequencies, they can't drive anything, which is why we see the drop-off here. But then at the high frequencies, when they become lower impedances, then they shunt down the line, and our SWR starts to rise. So this isn't really that good of a circuit either. Finally, we could take a circuit with inductors in it, but what we'll find with an inductor circuit is almost exactly the opposite of what we find with the capacitor circuit. And what we find with the inductor circuit, I'm just going to delete a bunch of these components real fast and just do this. We're not going to correct for anything here at all right now. Whoops. Two inductors. Turns out the first inductor needs to be relatively large. Actually, it needs to be, let me close this off for a minute. It and get rid of some of these other components that are still just they're hanging around from the last circuit. Maybe that's good enough. Okay, R2 is still there. We'll get rid of R2 also, but okay. In a circuit like this, the SWR doesn't show right now because it's the inductance is 0. Let's make L1 about let's make it say 20 microhenries, and L2 could be like maybe 2 microhenries. What we see is we see SWR that's pretty good at high frequencies and is terrible at low frequencies. And see if we can get close to our 40 dB number here. Okay. We have the exact same problem, the exact problem we had before, except this needs to be. There's our 40 dB law, 40 dB coupling factor. It's good at low frequencies. The SWR is bad at low frequencies. 20 microhenries is not nearly enough. I cannot balance that out with capacitors. I need something more like 100 microhenries if I wish to get down to 1 megahertz. And this would be 1 microhenry. Now we have our 40 dB coupling factor at low frequencies. Our SWR is modest. We could compensate for it with some series capacitors. We have a problem at the high frequencies where there's just the impedance becomes so high you can no longer drive 50 ohms. The other problem I have with inductors in general is going from 1 megahertz to 300 megahertz. These inductors are going to go through resonance. They will all go through resonance. This 100 microhenry one may go through resonance a couple times, and my experience has been that that's just a bad circuit. So all the voltage monitors that we looked at so far, with the exception of the resistive one, have problems. I could change this to be a transformer, or I could change this to be an auto transformer or a coupled transformer. And I'd have the same problem with the 100 microhenry inductor here. It just is, it's too much inductance at 300 megahertz or even 100 megahertz or 50 megahertz to not have gone through resonance. So we're kind of stuck with none of those as being acceptable. I'm going to end the video right now, and I'm going to do a part 2 here. And part 2 will start with the current monitor and the power monitors. And we'll look and see if some of those will be more suitable to what we want to do. If anyone watches this video before I post the next one and you've got a circuit that you like better than the ones I've mentioned, please let me know. Or if after I post the next video, which will only be a day or two here, let me know, and I'll include that circuit if it's something that works out. If it doesn't work out, at least I'll get back to you and we can discuss what was good or what was bad about it. But the voltage monitoring circuits don't appear to be that good, in my opinion, for what I want to do. So we'll proceed on. Thank you very much, and there'll be a follow-on video.